So we know that water can act like an acid or a base. It can either donate a hydrogen or accept it. So what if we have a reaction where one water donates a hydrogen and the other accepts it? So we're going to establish this equilibrium that you can see here. This is called the self-ionization of water because, as the name implies, water is ionizing itself. So we get H3O plus and OH negative as the products. Now, we can also set up an equilibrium expression. So Kc equals H3O plus times OH negative. Of course, we remember that we don't always write liquids in the denominator, but if we do, we get this equation. Because that is a very small equilibrium that sets up, a very small number of water molecules actually self-ionize. And so the H2O in the denominator is actually a constant. So if we multiply both sides by that, and since H2O squared is a constant and Kc is a constant, we get a new constant, and we're Kw. So this is called the ion product expression, and Kw is called the ion product constant. This is an important equation to remember. Kw equals the concentration of H3O plus times the concentration of OH negative. The H3O plus, remember, can also be H plus, so sometimes you might see this shortened to Kw equals H plus times OH negative. At 25 degrees Celsius, the value of Kw is 1 times 10 to the minus 14. And we're pretty much only going to worry about it at 25 degrees Celsius in this class. Okay, so if you put that in, right, like any equilibrium constant, it varies with temperature, but we're only going to worry about it at 25 degrees. All right, so now, so like I was saying a minute ago, H plus, we can put H plus in terms of H3O plus, and we get this expression. Since if you have pure water, the amount of H plus will equal the amount of OH negative because it's all 1-to-1. It's a 1-to-1 ratio. And so if you have the Kw and pure water, you can actually calculate what the H plus and the OH negative concentrations are in pure water. So 1 times 10 to the minus 14th, since we know that H plus equals OH negative, we're going to call them both X. If we take the square root, we get 1 times 10 to the minus 7th. So in pure water at 25 degrees Celsius, the H plus concentration equals the OH negative concentration equals 1 times 10 to the minus 7th. So that's a neutral pure water. All right, now the nice thing about this equation is that you can add acid or base or salt or whatever to this water. The H plus and the OH negative may no longer be constant if you add, or equal to each other if you add other things. However, the Kw expression will always hold no matter the solution. So 1 times 10 to the minus 14th equals H plus concentration times OH negative concentration will always be something that you can use regardless of what else is in the water, as long as it's an aqueous solution. All right, so remember that in a neutral solution or in a pure water, H plus is 1 times 10 to the minus 7th, which also equals OH negative. That's a really tiny number. So if you're talking about a solution where you have a strong acid, and remember a strong acid is defined as one that completely ionizes, generally we can ignore the amount of H plus that's around from the self-ionization of water because it's so much smaller than the H plus from the acid. So if we have a strong acid, we can determine what the H plus concentration is from the concentration of the strong acid because again we know the strong acid completely dissociates, so the concentration of the actual acid will also equal the concentration of the H plus. And that the amount of H plus from self-ionization is still there, however, it is so small compared to the H plus that it's negligible. But remember that there is still a very small amount of OH negative ion around as well because of the self-ionization of water, and so you can still use that equation. Okay, so let's do an example. Calculate the concentration of OH negative ion in a 0.1 molar HCl solution. Okay, so because HCl is considered a strong acid and completely dissociates, we know that the H plus concentration is equal to the HCl concentration, which is 0.1 molar. All right, there's the dissociation of acid, complete dissociation. So if we substitute 0.1 in for H plus, we can find the OH negative. So here, 1 times 10 to the minus 14 equals 0.1 times the OH negative concentration. So if we divide both sides by 0.1, so we get 1 times 10 to the minus 14 divided by 0.1 gives us 1 times 10 to the minus 13th molar OH negative. You're always going to be able to find one if you know the other, H plus or OH negative. Another example, let's say you have a strong base. So again, for a strong base, you can normally ignore the self-ionization of water as a source of OH negative because the OH negative from the water is so much smaller. So the OH concentration is determined from the strong base concentration. However, the self-ionization does still exist, and so the small amount of H plus ion will also be present, and you can find it by plugging in to that same equation. So, for example, calculate the concentration of H plus ion in a 0.010 molar NaOH solution. Okay, because we're starting with 0.010 molar NaOH, which is a strong base, we know that the OH concentration will also equal the 0.01, same as the NaOH, because it completely dissociates. So if we substitute the OH negative 0.01 into the ion product, we get this. Solve for H plus, and we get 1 times 10 to the minus 12th molar. I do want to caution you that there are 3 strong bases, the CaOH2, SrOH2, and BaOH2. When they dissolve in water, they do completely dissociate, but don't forget, because there's 2 OHs for every positive ion, you have to double the OH negative concentration before you plug it into the equation. So remember that, say for example, CaOH2 completely dissociates, you get a Ca2 plus 2 OH negative. So the concentration of the OH negative will be twice that of the initial calcium hydroxide. Again, by dissolving substances in water, you can alter the concentrations of H plus and OH negative. We just saw that, the strong acid or strong base. And so you can actually have other compounds in a solution and still be considered a neutral solution. So it doesn't have to just be pure water that's neutral. But the definition of a neutral solution is any solution where the concentration of H plus and OH negative are equal to each other as they are in pure water. So the H plus and the OH are equal to each other. If you have an acidic solution, the concentration of H plus will always be greater than OH negative. And if you have a basic solution, the concentration of OH negative will be greater than H plus. So again, neutral, they're equal. Acidic, H plus is greater, and basic, OH negative is greater. Okay. We can also see, because obviously in neutral solution, H plus equals OH negative equals 1 times 10 to the minus 7th. So in an acidic solution, the H plus will be greater than 1 times 10 to the minus 7th, and OH negative will be less than that. In a neutral solution, as we said, H plus is going to equal OH negative, is going to equal 1 times 10 to the minus 7th. And in a basic solution, the H plus will be less than 1 times 10 to the minus 7th, and the OH negative will be greater than 1 times 10 to the minus 7th. So we can quantitatively describe the H plus. Usually scientists will use, those numbers tend to be kind of bulky, and 1 times 10 to the minus 7th or whatever. And so it's more convenient to give acidity in terms of pH. So let's talk about how you can find the pH. Okay, the pH of the solution is just defined as the negative log of the hydrogen ion concentration. So actually, when you put that little p in front of the H, that's just describing a function, just like y equals 2x. That's a function where you would say, okay, y is just going to, you just take x and multiply it by 2 to get y. In this case, you're just going to take the H plus concentration, take the negative log of it, and you get the pH. So it's just a function. And actually, the p in front of anything just means take the negative log of whatever comes after it. So if you have a hydrogen ion concentration of 1 times 10 to the minus 3, what does the log do? It just takes that exponent, remember. So 1 times 10 to the minus 3 is the same as 10 to the minus 3. So the negative log of that is just 3. Note that the number of decimal places in the pH equals the number of significant figures in the hydrogen ion concentration. So here there's 1.0 is 2 significant figures, and so 2 decimal places is the same as 2 significant figures. So we don't count the 3 in our significant figures. Now in a neutral solution, you take the negative log of 1 times 10 to the minus 7th, and you get a pH of 7. So what does that mean? Since for acidic solutions, the hydrogen ion concentration is greater than 1 times 10 to the minus 7th. But remember that greater will just mean a smaller negative exponent, right? So the pH is going to be less than 7 because a number greater than 1 times 10 to the minus 7th will actually have a smaller negative exponent. So a basic solution will have a pH greater than 7. And of course, a neutral solution will have a pH of 7. The next figure just shows the pH scale and the pH values for some common solutions. And so you just might be interested in that. Blood is slightly basic, milk is slightly acidic, seawater slightly basic. Baking soda is basic, etc. Carbonated water, so like your sodas, have a pH around 4. Beer, also vinegar. You can just look at that. So we've been looking at logarithm. Remember, the logarithm will be the same as the positive exponent if the first part of the exponential number is 1.0. Of course, in this case, we have 2.9 times 10 to the minus 4th. However, just keep in mind that your number should be somewhat close to 4 in this case. So if you've got your concentration somewhere around 10 to the negative 4, then your pH should be somewhere 4. In this case, it'll be a little bit less than 4. So that'll give you an idea if you're putting in your calculator right. Do be careful, just as an aside, when you're dividing by a number in scientific notation, make sure that you are either using your calculator scientific notation function, which is usually the EXP button or the EE button or something like that. So if you were putting this number 2.9 EXP negative 4, put it in your scientific notation. If you are using your calculator where, especially if you have a fancier one, if you're putting it in as 2.9 and then you're hitting the times button and then you're hitting the 10 with the little caret and the negative 4, that's perfectly fine, but I highly recommend that you put that number in parentheses if you're going to do it that way, because your calculator now is separating those two numbers out. It's taking the 2.9 and it's multiplying it by 10 to the minus 4th, which is fine. But if you mean that to be the whole number and you're dividing by that, your calculator will not do it correctly. So make sure and use your EXP function on your calculator. And if you're not sure, maybe look it up online, or ask me about it. Come by, or in lab or something like that. Make sure you're using your calculator right. You'll know that you're not if your number is not coming out exactly right, but you're close but not exactly right. All right, so anyway, in this case, what is the pH of orange juice with a hydrogen ion concentration of 2.9 times 10 to the minus fourth? Well, the pH is just the negative log of the H plus concentration. So you're just taking the negative log of 2.9 times 10 to the minus 4. Like I said, it should be somewhere around 4, and it turns out to be 3.54. Again, two significant figures. The 2.9 should have 2 decimal places. The pH of human arterial blood is 7.40. What is the H plus ion concentration? Well, you're going to have to undo your negative log. So since pH equals negative log of H plus concentration, the H plus concentration will be the inverse log or the anti-log of the negative pH. So what is the anti-log? The anti-log is 10 raised to the negative pH. So that's another way of looking at it. So inverse log of negative 7.4 will be, so you can see here, H plus equals 10 to the negative 7.4, which is actually an okay way to write it. But if you want to, we like to put it into correct scientific notation. And so 10 raised to the negative 7.4 is the same as 4.0 times 10 to the minus 8th molar. Don't forget your units of molar. Okay, so it's the inverse function. Again, if you have a fancy calculator, you can hit 10 caret negative 7.40. If you're not sure how to do it, it's generally the button above your log button. So it's the inverse button, which is maybe in another color above your log button. So you would have to hit the second or the shift log to get that. You can do a calculation similar to pH for the hydroxide ion concentration, which is called the pOH. And so the pOH is just defined as the negative log of the OH negative concentration. So that's the same thing. Then because Kw equals H plus times OH negative equals 1 times 10 to the minus 14th, if we take the negative log of both sides, the negative log of 1 times 10 to the minus 14th is 14, so that's on the right-hand side. The negative log of the product, H plus times OH negative, if you remember your rules of logs, the P of H plus times OH negative is the same as negative log H plus negative log OH negative. So the you can take the negative log of both of those and add them together. So we get pH plus pOH equals 14. And that's derived from this same equation here, but what's really helpful is that you can see that the pH and the pOH are opposite. So if your pH is 3, that means your pOH will be 11. If your pH is 7, your pOH is 7. If your pH is 9, your pOH is 14 minus 9, which is what? 5. So don't get confused if you see the pOH. If pOH is less than 7, then it's basic. If pOH is greater than 7, it's acidic. All right, so an ammonia solution has a hydroxide ion concentration of 1.9 times 10 to the minus 3 molar. What is the pH of the solution? There's actually a few ways that you can do this, but probably the easiest way would be to find the pOH. So pOH is negative log 1.9 times 10 to the minus 3, which is 2.72, and then just subtract from 14. So pH is 14 minus 2.72 gives you 11.28. You could use the other equation as well. They're both the same equation, just written slightly differently. So you could actually find the H plus concentration. H plus times 1.9 times 10 to the minus 3 will equal 1 times 10 to the minus 14. Divide 1 times 10 to the minus 14 divided by 1.9 times 10 to the minus 3, and you get 5.26 times 10 to the minus 12. And then if you take the negative log of that, you also get 11.28. So you could do it either way. You could either first find the H plus concentration and then find the pH, or you can find the pOH and then subtract from pH. They're the same idea. We can measure the pH of a solution by using a pH meter, which you may, if you haven't already done so, you might get to do it in lab. We can also use acid-base indicators to measure pH because they often change within a narrow pH range. Here, and you can see some color changes of various acid indicators. So here's some good. If you haven't done it already, we'll be using some of these in lab, but you may have already probably used maybe phenolphthalein turns from colorless to pink at around pH a little above 8. Bromothymol blue changes from yellow to blue right around pH 7. Those are the most common indicators that we use. So there's a picture of a pH meter. If you haven't already, you'll get to use one in lab. What should you be able to do in this chapter? You should be able to identify what species is an acid and what species is a base. You should be able to find the conjugate acid and from a base and find the conjugate base from an acid in the Bronsted terms. You should be able to identify Lewis acid and base species if I ask you specifically which is a Lewis acid, which is a Lewis base. Be able to decide whether reactants or products are favored in an acid-base reaction. Remember, in that case, you're always going from the stronger acid and strong base to the weaker acid, weaker base. So you need to identify which is the acid on each side of the reaction and then which one is stronger. So there'd be different ways I might tell you which one is stronger, but remember that the equilibrium always favors the weaker acid. It always goes to that side. You need to be able to determine which acid is stronger depending on either its size or electronegativity. We went through that exercise by looking, remember that an acid, binary acid gets stronger as you go down a column, but an oxo acid gets stronger as you go up the column. Acids get stronger if you go from left to right on the periodic table. Be able to calculate the concentrations of H plus and or OH negative in solutions of strong acid or base. Be able to calculate the pH from the H plus or the OH negative concentrations. And you probably also want to be able to calculate the pOH, and then you'll be able to calculate H plus or OH negative concentrations if you already know the pH.